This video is produced by Shaun and
Kevin Burgess.
to support the workbook Sophomore Organic Chemistry 1 by Inquisition, available from www.byinquisition.org.
If I take out a CH in benzene and substitute it with a nitrogen, I get
Pyridine.
and a 5-membered ring involving an oxygen, which is also aromatic, is called
Furan.
If I substitute benzene with a methyl group, the trivial name for that is
Toluene.
and if I substitute with a hydroxy methyl
Benzyl alcohol.
or an OH,
Phenol.
Paraxylene has 2 methyl groups arranged opposite each other, which is para. Another way to describe that is
1,4-dimethylbenzene.
good. And if I substitute a CH on benzene with an amino group
Aniline.
or an aldehyde,
Benzaldehyde.
if I substitute with a vinyl group,
Styrene.
and if I polymerize that,
Polystyrene.
good. Tosic acid is a trivial name given to this compound which has a paramethyl relative to a sulfonic acid. Benzoic acid is the carboxylic acid derivative benzene. 1,2-dimethylbenzene could be described as,
Orthodimethylbenzene.
and meta-dichlorobenzene could be described as,
1,3-dichlorobenzene.
good. So I use para-bromobenzoic acid in a name to show everybody that the bromine group is oriented para to the acid functionality. Tell me another name for orthobromovenol, Shaun.
2-bromophenol.
Okay, and here are some other derivatives of styrene, putting phenyl groups on a benzene in a meta orientation, or phenyl group on an iodobenzene. All very obvious to name these things. And see how we're using methyl group as an abbreviation for these substituents here, and benzyl group for an abbreviation to CH2PH or CH2 aromatic ring. Para-dimethyl amino bromobenzene, or you could say para-bromo N,N-dimethyl aniline. Chlorobenzene, tertiary butylbenzene, nitrobenzene. All very straightforward. So to me, it's quite obvious that we should call this compound 3-phenylheptane. We start counting from the end that's closest to the substituent, and then so on. We can name the compounds systematically in this way. Now, based on those names, if we just take the fragment and add it, then we effectively saying here, for instance, that a phenyl group on hydrogen is benzene. Shaun, if someone came up to you on the street and said, hey, do you want to buy a bottle of phenyl group? Are they trying to trick you? Can you buy a bottle of phenyl group?
No.
You can't, because a phenyl group is just a fragment of a molecule. And similarly, a benzyl group is a phenyl and then CH2 attached to something else. Or a 1-naphthyl group is this fused benzene ring system here, attached at the first position to something else. You can't buy fragments, you have to buy the full molecule. In the book, there are lots more examples of aromatic compounds named in this way. Now, a key thing about aromatic compounds is if we measure the heat of hydrogenation, then we get less than we would predict. So the heat of hydrogenation of cyclohexene going to cyclohexane is minus 118 kilojoules per mole. For the diene, it increases again in about the same amount, and extrapolating that, we would expect the hydrogenation of benzene to give us back 356 kilojoules per mole. In fact, it gives back less, and that's because benzene is
Aromatic.
and therefore more
stable
than
expected.
Than expected, yes. Now, a critical thing about aromatic compounds is they are more stable than expected because of the molecular orbitals involved. So in benzene, if we take the 6 p orbitals, are they parallel, Shaun?
Yes.
And they overlap, don't they?
Yes.
Because the ring is planar. We can overlap them all with the signs of the Schrodinger wave equation the same, and we get a really stable molecular orbital. Or we can introduce one no and get 2 less stable molecular molecular orbitals, but they're degenerate. They have the same energy. 2 nodes gives us 2 more molecular orbitals, higher in energy. And 3 nodes gives us another one. Then, having got the molecular orbitals, we think of them as a bookshelf with no books in it. And the books are electrons. We have 6 electrons, 1 from each p orbital to place, and we pop those in the lowest molecular orbital available according to Hund's rules and things like that. So when we do that, the energy of the whole system goes down because we fill up the bonding molecular orbitals first. We can apply this concept to other rings. So for the cycloheptatrienyl carbocation, it has 7 molecular orbitals. Is it planar?
Yes.
And is it conjugated?
Yes.
And how many electrons does it have?
6.
And that is what we call a Huckel number. Huckel is a 4n plus 2 pi electron system. And that 4n plus 2 really comes from the molecular orbital diagram. Okay, then if I take a look at cyclopentadienyl anion, is the structure planar?
Yes.
How many electrons to place?
Again 6.
Is that a Huckel number?
Yes.
And so is it aromatic?
Yes.
And so is it easy to form this anion?
Yes.
It is. Whereas a similar analysis of the corresponding cation, which would be cyclopentadienyl cation, it has only
4 electrons.
So it's not a Huckel number and it can't be aromatic. If we look at the cation of cyclopropene, how many electrons to place?
2.
And is it aromatic?
Yes.
If I make the corresponding anion, how many electrons?
There should be 4.
And therefore it's
not aromatic.
not aromatic. And if I make the radical, how many electrons?
There will be 3.
And is that aromatic, Cheon?
No.
Good. Now, rings must be present for a compound to be aromatic. So is hexa 1,3,5 triene aromatic?
No.
Because the orbitals don't join up in a cycle. But they do in benzene. How about in cyclohexa 1,3-diene?
No, they have only 4 electrons.
Only 4. Yes, good. And then the orbitals are not joined up either. And what about in cyclopentadiene? Is that aromatic?
No.
But what if we deprotonate it?
It will become aromatic.
Good. There's some more examples in the book, but I think that's enough.